Hello there and welcome to the KC Science Hub. In this video, we shall be discussing 5 intriguing problems which appeared in the 2023 edition of the KC Annual National STEM Competition for A-Level Mathematics. First, we look at question 1 to 3, which were based on this diagram where we have a wavefront of light approaching a plane vertical mirror and it is reflected perfectly. So question 1, determine the equation of the reflected wave. And then for question 2, the candidate was supposed to find out what angle this incident wave makes with the normal from the mirror. And then in question 3, to find out how much the reflected wavefront is rotated from the incident wavefront. Next, we look at question 6, where we have this scary looking infinitely nested radical. And the student is supposed to determine the range of values of x for which this radical converges. Finally, we look at question 9, which is a seemingly trivial question where the student is supposed to count the numbers between 100 and 700 that contain the digit 3. So stay with me as I take you through these problems. So we jump right off with question 1, where we have this wavefront of light approaching a plane vertical mirror. For ease of understanding, we're going to make use of black lines to represent the approaching wavefront and green lines to represent the reflected wavefront. Now, our approaching wavefront has been defined by equation y equals k minus root 3x, and this is just the equation of a straight line in the xy coordinate system with gradient negative root 3 and y-intercept k. Now k is what is responsible for the propagation of this wave, because as k changes, then this line is being transformed and is being shifted along the axis, and we're going to see exactly how. So we're just going to call k our propagation factor. Now notice that for k equals 0, the wavefront would have been at the origin, still approaching the mirror, and for k equals 1, the wavefront has shifted nearer, and for k equals some positive h greater than 1, again the wavefront has moved nearer. So all what we're doing is we're just transforming the line. Of course, we're just making use of arbitrary values of k here. In a real situation, k would have to depend on the frequency of the wave to make sure that it moves equal distance in equal time, so that we have our wave being periodic. But of course, all we're doing is just applying a transformation, and particularly what we're applying here is a vertical shift of this wavefront. So when k equals 1, the graph of y equals negative root 3x is just shifted up by factor of 1, and again when k equals some general value h, we have that the graph has been shifted upwards by those same number of units h. And so the interesting property of straight lines is that a vertical transformation also means a horizontal transformation. So as the wave moves upwards, so it also moves forwards towards the mirror. And I think this is a really beautiful property of straight lines to observe. And we can show why this happens by just rearranging the equation of the wave to look like this: y equals negative root 3 into x minus k on root 3. So we find that each time we shift the graph upwards by k unit, so also we shift the graph forwards by k on root 3 unit. Now, for those interested in the nature of k, by some simple reasoning, we can get k to be defined as k equals root 3 t, where t is time, f is the frequency of the wave, and lambda is the wavelength. Suppose our approaching wavefront makes an angle beta with the mirror, then we're going to call this angle beta our angle of incidence, and by the law of reflection, the reflected wavefront must then make the same angle with the mirror, so that we have angle of incidence and the angle of reflection being the same. Now our reflected wave, which is in green, we hope to define its equation, and to do this we're going to need to know what angle that the reflected wavefront makes with the horizontal. But first, let us find out what angle this incident wavefront mixed with the horizontal. So we want to find out what the angles alpha and beta are. Of course, the angle alpha is related to the gradient of this graph, and so alpha can just be determined by alpha being the absolute value of the tan inverse of -√3, where -√3 is just the gradient of the line. Of course, we remember this from coordinate geometry, that the tangent of the angle that the line makes with the horizontal is related to the gradient in this way. And so we obtain alpha at 60 degrees, and consequently we obtain beta as just 90 degrees minus alpha, since they are complementary angles, and so we have that as 30 degrees. Now we go back to analyzing our reflected wavefront, which is in green, and so we define y arrow as mx plus c, where m is the gradient of the reflected wavefront. Now the reflected wavefront must also make an angle alpha with the horizontal, since it makes an angle beta with the mirror. And so we can determine again alpha to be, we can determine the gradient m of that line to be tan of alpha. Again, we recall this formula from coordinate geometry. So tangent of 60 degrees, which just gives us √3, and hence c is the propagation factor, again, as we saw from previously. And so we can conveniently say that the equation for the reflected wavefront should be given by y arrow equals √3x plus k, where k is just some real constant. Again, k must be defined in terms of the frequency of the wave and its wavelength. Now we move on to question 2, which asks, what angle does the incident wavefront make with the perpendicular to the mirror? And so we can construct the diagram in this way, and the angle of interest to us is theta, because that is the angle that the incident wavefront makes with the normal from the mirror. And we just see clearly that theta must be given by 90 minus beta, since again they are complementary angles, and so we just get theta to be equal to 60 degrees. Question 3 requires that we find out by what angle the reflected wavefront is rotated from the incident wavefront. We're going to make use of our horizontal axis as our reference point, so that we can measure direction in terms of angular displacement from the horizontal axis. Now we see that the angle of incidence theta I should just be this angle that it makes with from the horizontal, not with the horizontal. Now it makes the incident wave makes an angle alpha to the horizontal, but it makes an angle theta I from the horizontal, which is just given by 180 degrees minus alpha. And so we get that the direction of the incident wave is 120 degrees from the horizontal. And now for our reflected wavefront, since the angle alpha is just the angle that it makes from the horizontal, that is its direction. So we have that theta r, or the direction of the reflected wave, is given as alpha, which is just 60 degrees. Now, by how much the reflected wave is rotated from the incident wave is just the difference of these angles, the absolute value of that. So we have that theta r minus theta I, which just gives us 60 degrees. There are some interesting additional insights for problems 1 to 3 if we analyze them using rays rather than using the wavefront. I think that for A-level physics, optics or waves are usually taught using rays, and so we're going to analyze questions 1 through 3 again, but using this time rays and not the wavefronts themselves. Now we have our approaching wavefront again, which makes an angle beta with the mirror, and we construct our normal to the mirror in that way. Now for any point on the wavefront, the ray from that point is just perpendicular to the surface at that point. And so if we pick a point P on the approaching wavefront, then the ray from P is just perpendicular to the surface at that point in this way, and so the ray from P looks like that. And by geometry we can just show that this angle that this ray makes with the normal is just beta, the same as the angle of incidence which we talked about previously. And again, by the laws of reflection, the reflected ray must also make the same angle beta with the mirror, or with the normal. And so again, if we use the same idea that this ray must be perpendicular to the surface from which it is generated, then we see that the reflected wavefront must be that way, so that the reflected ray is perpendicular to it. And again, how do we find then the equation of the reflected wavefront? By this construction, we can determine the angle alpha, which is the angle it makes with the normal to the mirror. And the normal to the mirror is just another horizontal axis. And so the angle alpha is the angle that the reflected wavefront makes with the horizontal. And so we can just get the gradient of the reflected wavefront as tangent of alpha, which is the same solution we got using the other method of analysis. Now problem 2, which asked what angle the incident wavefront made with the normal to the mirror. Again, we can just quickly see that that angle is just going to be again 90 minus beta, which is just alpha. And now the angle by which the reflected wavefront is rotated from the incident wavefront is just this angle theta, which is just 2 times beta, and beta being 30 degrees, that just makes it 60 degrees. So yeah, there's some really fun insight if you want to look at the problem from the for using a ray analysis rather than using the wavefront themselves. We move on to question 6, where we have this infinitely nested radical, and we're supposed to determine the values of x for which this radical converges. So we've been told that this radical converges to some real number L. Now we're going to make use of some really important property of infinite mathematics right here. So we're going to say if we cut down this expression from here, moving onwards to infinity, it's still an infinitely nested radical, because of course it still goes on to infinity. And so we're going to make the claim that this thing inside here also goes to the same limit L. And again, I know it's not so intuitive to think about, but we're going to say that also goes to the limit L. Remember, it's the limiting process. One of these infinities is technically bigger than the other, but in the limiting process, both converge to the same limit L. I think that a similar thing was asked in the previous edition of the STEM competition, where we asked for what this infinite fraction converges to. And again, it's the same thing as looking at this under here and saying it's the same as what we were given to start off with. And so you have a thing divided by 1 plus itself, and so this thing under here converges to the same limit as the entire fraction, and so we're making use of that here. I think that that's the beauty of infinite mathematics, because we can escape with these little details. So moving on, we're saying this converges to L, but this in here converges to L too, and so we're saying that this problem just reduces to this equation, which becomes a quadratic like this. And for this quadratic, since L is real, we compute the determinant, which is just 1 plus 4 into x plus 2. And for real L, this discriminant delta must be greater than or equal to 0, which implies that 1 plus 4 into x plus 2 must be greater than or equal to 0. And so we find that our range of values of x for which this radical is going to converge is just x greater than or equal to 9 and 4. We then arrive at this final problem, where we're supposed to count the numbers between 100 and 700 that contain the digit 3. Personally, this is one of my favorites from the STEM paper, because it just looks so simple. Again, I love the thinking that goes behind the problem in solving it. The first thing a student might think about is just going between, for every 100 numbers, how many digits contain 3, and then multiply that by the number of hundreds between 100 and 700. And I think that many candidates choose this route to just okay, how many digits exist for every 100 that contain digit 3, and then just multiply that by the number of hundreds between 100 and 700, which is just 600 hundreds. The rather interesting approach I like is using this. So the number of digits containing 3 is just the total number of digits between 100 and 700 minus the number of digits not containing 3, which is really easy to compute, as we're going to see. So the total number of digits between 100 and 700 is just 600, minus the number of digits that don't contain 3. Now we have 3 spaces to fill since all of them are 3-digit numbers, and so this first space can only be filled in 5 ways, because we can only either fill that first space with the number 1 or the number 2 or the number 4 or the number 5 or the number 6. Now the second can be filled in 9 ways, that's excluding the digit 3, and the third again can be filled in 9 ways, and so just 600 minus 5 times 9 times 9, which just tells us that the number of digits containing 3 is just 195, which is the same thing that you get if you just go and count manually. But the reason I'm going to discourage the manual counting is, of course, this is an easy situation where the number of digits is not so large. Suppose you are supposed to count between 0 and 30,000, the number of digits that contain 3, then it becomes a challenging problem to just use the method of counting how many numbers in every 1,000 perhaps are going to contain the digit 3. It becomes more troublesome to think about, and so I think that is a more elegant approach. It's what I would advise. So we've come to the end of that today. Thank you guys for watching. So if you enjoyed our video, consider liking the video, subscribing to our channel, and turning on the notification bell so that you get notified whenever we obtain